this next session of the OzGrav live stream talks. OzGrav is the ARC Center of Excellence for Gravitational Wave Discovery based in Melbourne, Australia. And we've been excited for the last couple months bringing you these live stream talks as a way to bring the research science of our great scientists out into the world. These talks showcase our researchers and give them this opportunity to share the science that they love. So today we have with us Avi. Avi is a PhD student at Monash University and is a member of both our OzGrav collaboration as well as the larger LIGO scientific collaboration. He did his schooling in both New York City and Calcutta, so he's definitely well-traveled. His area of research that he's interested in is looking for really big black holes, so ones that are more than 100 times more massive than that of our sun, and figuring out what we can learn from them and what that tells us about how the universe formed. And in addition to doing this great research, Avi, in his free time, also enjoys programming video games. He enjoys rock climbing as well as salsa dancing. So during this talk, you'll have the opportunity to put questions in the YouTube chat. And at the end of his talk, we'll pass these questions on to Avi and he will answer them for you. So please don't hesitate to engage with that chat on YouTube. So now, without any further delay, Avi.
Hi, thanks Jackie for the intro. So today I'm going to be talking about how we can use parallel computing to understand our universe. First, I'll actually talk about what parallelism is, and then I'll give a small example of parallelism with the Nbody system, which is basically a system with many particles, like the images on the right of this plot, of this slide. After this, I'll show some videos comparing when we use parallelized code versus when we don't. And then finally, I'll talk about some uses of parallelism in astrophysics. Okay, so to start, I'd like to share a story that relates to the concept of parallelism. When I was a 5-year-old, I really wanted to build a sandcastle to reach the moon, and I really thought I could do it. Sadly, I wasn't too successful. Thinking back on it now, I see that there was one obvious reason why I couldn't do this, and it was because I wasn't able to build the tower fast enough. Now, there's some ways I could have built the tower a little faster. First of all, I could have probably just worked a little harder and tried to double my piling speed. I could have also tried to hire a crane to help with the addition of dirt onto the tower. And there is one more method. I have an elder sister and parents. Perhaps I could have convinced them to help me with my project. This approach would have probably been the most productive for me, as I could keep adding more and more people to help me finish my project. Each of them would be doing the same work, but in parallel. And although I was unable to build my tower, the different things I could have done to speed up my progress can teach us how to speed up the computer processors. And computer processors are actually the part of computers that do the math and the work behind all of our programs. So each of the three techniques of piling dirt faster onto our tower relates to how we can speed up our computer processors. So here are some of the analogous methods to increase the speed of computer processors. So speeding up my work relates to making the processors faster. Getting better tools relates to improving the components of the processor. Hiring assistants relates to adding more processes altogether. Okay, so this is a plot of the speed on the y-axis, the speed of the processor on the y-axis, and the year on the x-axis. What this shows us is that from the 1970s, we've been trying to increase our processor speed. And we can see that in the first few years, we did pretty well. Till 2000, we were increasing the speed of the processors pretty well, and it was almost increasing really quickly. But now, between 2000 and now, it seems like we haven't really made much improvement in the speed, right? And you can think of the speed of the processor kind of like the speed at which electrons are moving through the processor. The last few years, the speed of the processor has remained constant, and this is because increases in speed results in increases in the heat of the processor itself. And so eventually, the faster you go, the more heat will be applied to your processor. And so this is an issue because It's basically just too hot. Now, the second method was to improve the components of our processor. So the idea is that we want to improve the internals. By improving the internals, we're in a way increasing the number of highway lanes on our processor for the electrons to move through the processor. But this is kind of interesting. It's like you're increasing the number of highway lanes, but you're keeping the width of the highway the same. So what's going to happen is that electrons are going to be going down their highway, right? But they need space. And eventually, when you keep on narrowing the highways, the electrons are going to get upset because there's just not enough space for them. So the issue here is the quantum limit. Basically, we can't make our the lanes too small because we'll get issues with we'll have some issues with our electrons. Finally, we have a method of adding more processors. So initially, we just had one processor, but instead of just one, if we just add a few more processors, we'd be able to do much more work, right? But there is a small caveat to this, and it's that these processors might need to be a little less powerful than the original big one, right? In the past, the father of supercomputing, Seymour Cray, has been quoted to say, "Would you rather plow a field with 2 strong ox or 1,024 chickens?" Because he thought this idea of adding more smaller processors was kind of absurd. He thought that it was obvious that developers would want the 2 strong ox rather than the 1,024 chicken, that they would want the 2 powerful processors rather than the 1,024 smaller processors, right? But this was before parallel computing became popular, I guess, because we've kind of started using the 1,024 chicken. Okay, so now that we've spoken a little bit about the conceptual understanding of what parallelism is, I thought we could talk a little bit about the computer hardware that goes into allowing this to happen. So this is a small diagram of a CPU, what's known as a central processing unit of a computer. The CPU has some input. That's where you type in your keyboard, your mouse, all that stuff. And then those inputs go into your CPU. And all the maths that the CPU does is done by the ALU, which is known as the arithmetic and logical unit. Once all this stuff is done in the CPU, the processing is done, it can then display some output on your monitor, right? So like the CPU, we also have what's known as a GPU. A GPU is a graphical processing unit. It has some similar components, except for it has a lot more ALUs. And notice that its other components are kind of smaller. And its ALU is also smaller. So a GPU is basically similar to a CPU, but it has way more many ALUs, the arithmetical and logical unit. Now, the reason why these were even made in the first place was for video games. In video games, we have a lot of 3D worlds, right? And to actually display a 3D world on your computer screen, you need to move the 3D world onto a 2D screen, right? And so this mapping of 3D points, the vertices, into the rendered model on your screen requires a lot of math, but it's a lot of basic math. And so the idea was that initially you take all the graphics that are being processed by the CPU, the one ALU for the CPU, and you instead give it to the different ALUs of the GPU. So earlier, what was happening is that your screen was being rendered pixel by pixel by the CPU, one by one, right? And now your GPU has many ALUs. And so what it can do is it can kind of process each pixel simultaneously. So this was why we even made GPUs in the first place. After this came around, some people started thinking, can we use this in simulations and not just video games? And so I'd like to talk about what's known as the Nbody simulation and how we can use parallelism in these simulations. So an Nbody system is basically a system with a lot of particles, right? So we can consider this as an Nbody system. So these are a bunch of circles, right? And imagine that we're looking at these 5 circles in particular. And let's consider the interactions between these 5 circles, right? So the number 1 interacts with these others, right? It has 4 interactions. And number 2 also has 4 interactions, right? And so on, we basically have each of them interacting with each other. And so if we have a system of n particles, then the number of interactions is n squared, n times n. Now, what we want to do is we want to process the interactions first on a CPU and then see what it would be like to process it on a GPU. Okay? So what we're going to do is we're going to take all the particles, line them up one by one, and pass them to the CPU. This is known as sequential processing because we're passing in one by one to the CPU. We can also take these particles and divvy them up amongst the ALUs of the GPU. And so each particle is going to be processed by one ALU of the GPU in parallel. So let's see how this goes. Now, because the GPU has way more ALUs, we're processing the particles in the GPU much faster than the CPU. In fact, on the GPU, it's done in what's known as 2 clock cycles, but on the CPU, it's taking all 8 clock cycles because it's processing sequentially. It needs to wait for the first one to be processed before it can do the second particle, and so on. So now that we understand this concept, let's try to look at it in an actual simulation. So here's a small simulation of an Nbody system using where the force between the particles is gravity. Now, both these are actually running. The one on the left is a sequential version, and the one on the right is a parallel version. The sequential version is way slower. The parallel version is gone much further ahead than the sequential version, right? Now let's take a look at another Nbody simulation. So in this one, we're kind of modeling each particle as a bead. And each bead is kind of interacting and has like, it can collide with other beads. Now, again, the sequential version is running, I promise you, it's just running really slowly. The parallel version has just gotten much faster. Okay, so I would like to highlight before we move on that we still need CPUs. We can't like we can do all our math on the GPU, but we still need the CPU to do a lot of the basic setup and stuff like that. So essentially what's happening in these past two simulations that I've showed you is that all the main math, all the calculations for the collisions, the gravity, all that stuff is being done by the GPU, while the rest of the stuff is being done on the CPU. Okay, so we're not getting rid of the CPU, we're just using the GPU for the math and CPU for the rest of the other code. Okay, so now I thought we could talk a little bit about the uses of parallelization in astrophysics. So there's a couple ones that we have. There's quite a few, but I've listed 3. So we've already discussed Nbody simulations. Then there's also, we can determine the masses of black holes in a parallel way. And there's also looking for exoplanets. So for this presentation, I'll just get into what I work on, which is determining masses of black holes in parallel. Okay, so when we have 2 black holes, these guys are like 2 black holes which are spiraling into each other, right? They spiral into each other and then merge to form this big guy, right? This big black hole. In this process, there are these waves, known as gravitational waves, that are emitted from the black holes, right? And we have detectors on Earth, such as LIGO and Virgo, which can detect these gravitational waves. This plot here is a plot of the gravitational wave strain, and this is the reading that we can get from such an event of merging black holes. Now, from this data, from these lines, from this gravitational wave data that we've recorded, we want to try to figure out what the masses of these 2 black holes are and what the mass of the final black hole is, right? So one way we can do this is by trying to first fit the data with the prediction. So this orange line here on this blue data is our prediction, right? And so first we can try to fit the data with the prediction. We can then compare our prediction to the data. And if the prediction doesn't match, we want to repeat the process. Okay, so initially we predict that maybe the distance the black holes could be at like 800 megaparsecs away from us, and the total mass of the system could have been 200 times the mass of the sun, 200 solar masses, right? And we see that it's not quite correct, right? It doesn't look so nice. So let's try again. Based on this, let's try to improve our guess. Okay, let's decrease the distance. So initially it was 800. Let's decrease it to 605. Okay, seems to be getting closer. Let's decrease it a little bit more. Okay, so the distance seems to be matching up. It seems to be like this line here at least seems to be matching up, right? Okay, so we can work with that. Now let's try playing around a little bit with the mass, right? So, okay, let's make the mass a little smaller. So from 200, let's bring it down to 132. Okay, seems to be The fit seems to be becoming a little better. The prediction seems to be becoming a little better. Let's repeat this. Okay, so now we have a distance of 420 and a total mass of 65, right? And this line seems to be kind of matching up with the data. Our prediction seems to be kind of matching up with the data, right? Okay, so now that we have these two parameters done, the distance and the total mass, we can also adjust some other parameters that tells us things like the spin and the orientation of the black holes, and eventually we'll get a much better fit to the data, right? So our prediction can match the data very well. And so what this tells us at the end is that with our prediction, the data comes from a binary black hole system that is 420 megaparsecs away from Earth and has a total mass of 65 solar masses, right? So this is how we do what's known as parameter estimation. We're trying to predict what the properties are of this black hole system by using this method of fitting this data, right? Now, it gets a little interesting. This prediction comes from what's known as the physical model of the system, right? So we basically model these black holes, and we try to see when a black hole is of 420, when it's at a distance of 420 megaparsecs and has a total mass of 65 solar masses. This is kind of the way we expect to see, right? But we want to add more and more complex physics. Like we want to add concept of general relativity. We want to add as much information we know about the system into our model, right? So the more complex the physics is in the predictions, the longer it actually ends up taking. So this process that we walked through, it took kind of some time, right? Like we went through one by one. We iterated over our predictions. So we made one prediction, and then we edited it, and then we improved upon our prediction, right? Now there's another way to do this. We can make multiple predictions at one shot. So initially we made 5 predictions, right? Instead, what we could do is we could guess a whole bunch of different values for our predictions and see how well the predictions work. And then once we have made our multiple predictions, we choose the best prediction, right? And then we see how well that fits the data. And if it doesn't fit it too well, then we use that as a starting point, and then we repeat the process. So in this way, what we're doing is that we can basically drastically decrease our the time we need to take to make our predictions. In the previous case, what we were doing is that we were changing one value and then seeing how that affected our final fit, right? But now we can change a lot of different values and make a lot of predictions and use that to figure out how we can proceed with our final estimation of the masses. So just to give you guys an idea, recently I analyzed one gravitational wave event using this parallel infrastructure, and I used 540 processors. And it took a long time. It took 20 days, okay? It took 20 days to run in parallel. Now, sequentially, this would have taken much longer. If I ran this sequentially, and I didn't run this sequentially because it would have been impossible, it would have taken 30 years. So that's just kind of like an idea of how much power we can get if we can sometimes code our things in parallel. But I hope that was informative to you, and that's all I have for you guys. Do you guys have any questions?
All right, thank you, Avni, for that. And I especially like the illustrations that you did of your black hole with the biceps. Sorry. I like that one. So we had a question, and it was, how do you make sure the calculations are processed in the right order or come out in the right order?
1 second. Okay, so that's a good question, because it's very important to process the calculations in the right order, right? Because if you calculate, so say you're trying to calculate the force of, so basically what it gets down to is that you need to have your algorithm needs to be able to be able to run in parallel. So in this case, where we have interactions of Nbody system, we can actually have each we can calculate the force on each particle at any point in time, right? And it's independent of the other particles. So it's okay. So it doesn't actually matter if you process particle 1 or process 8 first. We just need to do them all. And once we do them all, can we take it to the next step? So it gets trickier for systems which are time dependent. So say that particle 1's position depended on particle's 6 position after we calculated or something. Then if it's time dependent, then we can't actually do it on a GPU. We can't actually do it in parallel.
And we have another question from someone you know, your friend Reinhold.
Okay.
And he says that you mentioned that GPUs have smaller ALUs so they can do many simple calculations. His question is, why does the size of the ALU mean it can do more complex calculations?
The size of the ALU is not necessarily the size. It's basically, it's kind of like you have more features and abilities that are available to you on your ALU itself. Like in the case for, okay, so I actually do have some diagrams that might help for this. So this is kind of what the internal of one of these processors looks like. You have some global memory, you have some constant memory, and then you have what's these small guys, these small classrooms almost, and these are the compute units. And inside these, you have the actual person who's doing the computing and the private memory of that guy. Now, what happens in a GPU's ALU is that all of these things are much smaller, and so they can't hold as much information and can't therefore do that many complicated tasks. So does that kind of answer your question, Reinhold?
We'll give him the chance to respond on the chat, but hopefully it does. And while he's doing that, we had another question come in. It says, are you involved in sifting out the actual gravitational wave signal from the noise? And if so, is that the thing that eats the processor time?
So there's 2 stages in gravitational, like there are quite a few stages, but one stage is we're continuously getting the data from the detectors, right? And the first pass of like trying to find stuff in the detectors is just looking for what's known as like, so basically the first stage is we just want to look through the data and try to see if we can see something that's wave-like, right? And only once we see, so we go through the data and we flag, okay, that thing could potentially be something that looks like a gravitational wave, right? What we do is we then focus on that area and we then do further analysis. And that's where my analysis comes in. I do like a focused analysis on something that we already think has something interesting. So what I'm analyzing might just be like noise, like some like blip in the detectors, or it might actually be gravitational waves, and that's what I'm doing to check. So that's what this process also tells us. So this fitting process tells us if it's a real gravitational wave or not.
Okay, great. And yes, Reinhold says yes, you did answer his question. Okay. So I think we're just going to do one more question. Again, the one I always like to ask, that here you are at the beginning of your career and with a lot of science lying ahead. So what is future discovery are you most excited about?
Well, I'm most excited about finding the big guys, the big black holes. And so far, we've only found, LIGO's only found what's known as stellar mass black holes, right? Black holes that like we know come from like when stars blow up. But we still haven't found so there's like 2 categories that we know exist. The stellar mass black holes, the ones that occur from when stars blow up. And there are these black holes that are supermassive, and they're way, way bigger. And that's the one that was photographed last year, right? Yeah. And so there are these 2 categories, but there's a lot of stuff in between that we haven't seen or like we know nothing about. And I think it'd be really interesting to find those. And I think it'll be possible to find them with LIGO. So.
All right, great. So thank you, Avi, for that talk. It was excellent, really very interesting. And what I'm going to do is I'm just going to tell you a little bit about our next live stream talk. It's going to be by Nbody, and she's going to chat with you in her online talk, Gravity and Physics, and share her excitement about those topics, which leads into her research with star cluster simulations and black holes. And it'll be just like this. You'll be able to ask questions live of Nbody during that talk. And then another one of our researchers, Paul, will be giving the AIP talk at 10 a.m. on July 3rd. So that is the Australian Institute of Physics. They have their own live stream series. And that is another opportunity for you all to hear more about OzGrav science. So thank you, Avi. And we look forward to seeing everyone out there at our next live stream talk.
Thanks. Bye.